variability. So you could generate a plot for any number of different items. How tall the wheat is in a field, how tall people are in this room, any number of things. And what we focused on, calculation of x bar, the average, was pretty trivial. But what was more important was variability. And we saw different curves, a broad curve, very variable population, a narrow curve, not as variable a population. And so we can ask, why is this population variable? Why does everybody have a different height? Why do different plants in the field have a different height? And there were two reasons. So why is this variability here? So genes and environment. I'll change your answer slightly. More than just polygenes, gene systems. And so these are the two reasons why a system is variable. And so it's nice to be able to split out and portion out that variability and ask how much of the variability is due to genes and how much is due to the environment. Remember, the measures of variability we have is sigma or S, which is the sample variability. We had SEM, which is variability of the population from which the sample came. And then at the end, very briefly, we had variance, which is similar to the sample variation. We're going to use variance today because the standard deviation doesn't allow us to divide and multiply different measures of variability, whereas the variance does. So the question is, why is this population variable? And the answer is, part of that variability is due to genes, polygenes, but also just Mendelian inheritance, where we have assortment, recombination of different combinations of alleles, and then the environment imposes a variability on a population. So the way in which we answer this question, why, is with heritability. Abbreviated as H. So heritability, H, equals V sub G over V sub P. Heritability is the proportion of sample variability due to genetic variability. Proportion of sample variability due to genetic variability. And that's what V sub G and V sub P is all about. V sub G is that part of the variability due to the genes divided by the total phenotypic variability. And so it's an unfortunate choice of words because heritability sounds like inheritance, but this has absolutely nothing to do with inheritance. This is all about the variability of a population. It has nothing to do with an individual. You can't measure heritability in an individual. This is coming out of population samples. And so be really careful how you use those terms. Everybody see the basics of what we're talking about? Any questions on what I mean by heritability? The proportion, so we get asked in this room, what proportion of variability in height is due to your genes? What proportion is due to the environment? That's what this is all about. Yes?
Is the V equal sample modified?
Varies. Population. It's the proportion of sample variation in the population due to genic variation. Let me give you a couple of examples of what I mean by that. So this is in cattle. White spotting, 95%, milk yield, 43%, conception rate, 3%. So just a couple of phenotypes out of a herd of cows. What that means is that the coat pattern is virtually completely due to the genes and alleles. Whereas milk yield, very, very different now. Milk yield is partially, almost half, due to the genes, but a significant, slightly more than half, due to the environment, which means temperature, which means how much food, which means the quality of food, which means how much water, all of that. And conception rate, very, very little is due to genes. There are very definitely genes which do control conception, as infertile couples know well, but mostly it's due to is there a male present. So how do we relate this to that curve? Well, let's start off with the population. Now remember, this is all coming from the way we started this out of selection. Where we're selecting for any trait that's selectable, like milk yield or the height of plants in the field, and we can select over a number of generations, but as we discussed on Monday, eventually we're going to run out of room to select. And we discussed that all on Monday, and so the curve is going to flatten out. So let's say that we wish to do that kind of a selection experiment, and we're going to take the individual from the end of the curve that we're interested in. If it's milk yield, those would be the cows giving the most milk. And we're going to use them in order to select a new population. They're going to be the breeders for the new population. So if we get a curve like that, that says that heritability is equal to about 1, which means that we're there on the yield curve. So we have a herd of cows. We don't know where they came from. We what the milk yield is, and we're going to start our own herd, and we're going to use as the breeders the cows that gave the most milk. And so early in this experiment, we're going to shift that population over so that the average is pretty close to what the parents were. Everybody see what we're doing? Later on, we could do the exact same thing. And now, we have not shifted the curve at all, because now we're up there on the selection curve. So it depends on where you are in the selection curve. This looks very obvious and very intuitive. Everybody knows you cannot select forever. So what that says is that when you're down here, that this variability is very high. The heritability is very high at that point. Whereas here, we're still variable, but now low heritability because we've already selected alleles to the max. Understand, I didn't say a single word about how many gallons of milk per cow here, or here, or here. Clearly up here, we've got more gallons per milk, but we have the lowest heritability. So heritability says nothing about the phenotype. Heritability is strictly only what proportion of the variability is due to the genes. The genic variability. It has zero to do with inheritance. Inheritance is at individual level. We don't know which one of these is giving the most milk. The assumption is, out here, this is separated in time.
So heritability has nothing to do with the what?
Inheritance. It is only variability. It doesn't say anything. This has low heritability, but on this curve it's showing the highest milk yield. This has the highest heritability, but has the lowest milk yield. So heritability is not measuring which herd of cows is better. Obviously, this is better than that, but it's just the opposite for heritability. Heritability has zero to do with an individual. It is population level only. If we have two herds of cows, Farmer Brown's and Farmer Jones, and you measure heritability, and one is a heritability of 1 and one is a heritability of 0, it still does not tell you which herd of cows is giving the most milk. two separate issues completely. This is only about Y variability. And it's an instantaneous measurement. The measurement of heritability going from here to here, or from here to here. What I mean by an instantaneous measurement is that if you do the measurement in the summer and then repeat it in the winter, you may probably and almost certainly will get a different heritability number. Not the extremes like I'm using here, but just a different heritability number. Because we're talking about the environment. And so the environment is different in the summer than it is in the winter. And so when you do a heritability measure, it's not a fixed measure. The genetic part is undoubtedly fixed, but the environmental part can fluctuate. And so even if you do a measurement the next day, and it's cloudy and rainy, you can get a different heritability estimate. You got a hand up?
Yeah, are those heritability values for those three phenotypes that you gave us just one measurement, or is that an average?
No. So we just took a herd of cows and did a measurement on it, without even telling you how we do the measurement. We'll get into that a little bit in a few minutes. Does everybody see what's going on? Heritability has nothing to do with inheritance. It's only measuring Y variability. It has nothing to do with an individual. A population that has high heritability is not necessarily better than a population that has low heritability. It has absolutely nothing to do with how good a population is. Only Y variable. I probably said that 25 times, trying to make sure that you understand the emphasis.
The third breakdown, do you get that by basically doing the same thing as with the second breakdown?
Yes, exactly. Right. So if you took that and made that population from the individuals that had the highest phenotypic trait. Someone else in the hand up? Does everybody understand? Population level, not individual, has nothing to do with the quality of the trait at all. This is only having to do with Y variable. There's an aspect of heritability that's actually quite controversial. That is heritability of human intelligence. And so the controversy isn't a scientific controversy. Scientific data is really well established now. But it's a political controversy. Because depending on whether heritability for human intelligence is high or low, a high heritability says that the greatest part of your intelligence stems from genetic variability and has little to do with the environment. Whereas a low heritability number says that environment plays a very strong role in the intelligence of a population. Remember, it's population. And so the reason that that's a political controversy is because if the environment has nothing to do with intelligence, it says that there's no point in having enrichment programs, nothing to do with pre-kindergarten classes and schools and nutrition has nothing to do with intelligence, that you're born with a fixed measure of intelligence forever. And so there was a study done, an English study, back in the 60s, that said the heritability of human intelligence was 80%. That's a pretty high number. So let's look at that. First of all, how would you measure the heritability of human intelligence? How would you be able to do that? Remember, if you're going to measure the heritability, you need to either keep the environment constant or keep the genes constant. That's a hint. Is that? You can't control the environment. What's that? I study. But you can't control the environment. So you can't look at the environment. What kind of twins?
Identical.
Identical twins. How would you do the experiment then? You're right. I mean, how would you do the experiment?
They've been separated at birth.
Identical twins separated at birth is a classical measurement, a classical mechanism to determine heritability of all sorts of things. And so this study in the 1960s, let me just go back and give you some basic data, because separating twins at birth or adoption just doesn't sound right today. But back in the 1960s, looking backwards 20, 30, 40 years into the Depression, into World War II, separating twins at birth to give up for adoption was routinely done, giving the two twins to different families, just because it was so difficult to find a family willing to accept any child for adoption. Accepting two children was almost unheard of. So the routine in the 1920s, 30s, 40s, it started to end in the 1950s, was simply to separate. That was just the routine in all of America, all of Europe. And so there grew up in the 1960s adults who had a twin separated at birth and raised separately. And so this became the population for a huge number of studies. One of my favorite was a University of Minnesota study about the 1970s, where they brought together twins separated at birth who had never seen each other. And each twin walked in wearing almost the same clothing, same hairstyle, like the same flavor ice cream, the same kind of jewelry, just incredibly similar in behavior. But we're focusing now on intelligence. And so that was the genesis of the study. Identical twins separated at birth. And so what exactly does it mean to measure the inheritance of intelligence? That's a really loaded question. What is intelligence? Commonly think of intelligence, oh, I have the IQ test, that tells me my intelligence. But how good is an IQ test? I know, so any psychology students are in here, I know that they now claim to have better IQ tests than when I was a kid. I'm not convinced, but maybe. So you give someone a test. How much does your answers on the test have to do with your intelligence? IQ tests, in fact, correlate really well with academic performance. Now, I say correlate. It doesn't mean that every student with a high IQ is going to be an A student. Some aren't. But it correlates well with academic success. It correlates well with success in life in general. But if Mozart couldn't add 2 plus 2, I think he would still be a genius. And so I think it's pretty clear, in my mind at least, that IQ tests, at least the generic mass-produced tests, do not measure every aspect of intelligence. You just know intuitively that some people are better at X than they are at Y. Better at music than they are at science. You're here, so you're better at science, maybe, than better at music. I certainly have zero music aptitude. Who's smarter, boys or girls? I love doing that. So, here's the story. There are some questions that girls do better at, and some questions that boys do better at. Did you know that the IQ tests are rigged? They are rigged so that the IQ of girls always comes out, just by coincidence, exactly the same as the IQ of boys. So, in a population, not individuals, I mean, clearly there are math wizards who are girls, but just population-wide, girls tend to do better at language-type situations, boys tend to do better with spatial numerical types of questions. Did you know if you were to take an Australian IQ test, you would come out retarded?
I think I would come out retarded in an American test, but...
Because there is a cultural aspect to asking questions, even in English. American English, British English, Australian English, eh, mate? There is a cultural bias in how questions are asked. In this country, even north versus south, urban versus rural, kids growing up on a farm versus kids growing up in inner cities. That's why I have not all that much confidence in our mass-produced IQ tests. I know that there are IQ tests that are very massive, very expensive, that parents can arrange for a child to take, that probably gives closer estimate of whatever IQ really is. Again, if Mozart couldn't add 2 plus 2, he'd still be a genius. So that's the problem, because the original question was, how do we determine the heritability of IQ, of intelligence? And the way we determine the heritability of intelligence is with an IQ test, mass given to kids in, I don't know, kindergarten, 3rd grade, 5th grade, and all that. So that's where I'm going with all this. So this English study came out at 82%. Sometime in 1960, sometime in the 70s or so, the guy had died. Somebody went back and pulled out the data, and he dry labbed it. He filled out all the forms himself and got the answer that he thought was most appropriate. And so 82% IQ is gone. Human intelligence is not that high. Now that study has now been reproduced dozens of times in dozens, if not hundreds of countries. And now heritability for intelligence and so all the numbers from all different countries, all over the world, English-speaking and non-English-speaking, average out, and really fall pretty close to 62%. So it probably what you might intuitively think, that there is absolutely a genetic contribution to intelligence, but the variability is really very high, and there is a large environmental variability. Understand that that doesn't answer the question, should government put money into preschool enrichment programs? There's there's no answer to that. That's a societal issue. But every now and then, you see heritability pop up. People who are against it usually use 80% number, which is a totally made-up number. And so, just something for you to think about. That heritability has nothing to do with the population being good or bad. It's just like the milk, just like the herd of cows. If you have a herd of cows with high heritability, it doesn't tell you that it's giving more milk. In fact, remember, the low heritability was giving the most milk. So heritability numbers cannot be used to judge how good a population is. And that's probably the most serious misuse of genetic testing that there is. It has nothing to do with it. Whether it's high or low doesn't mean that that population is more smart or less smart. It only has to do with variability. Have I pounded that in enough? Does anybody have any questions? Yes?
So low heritability is low variance? Or
Yes. So low heritability means that, where do I have it? That V sub G is smaller than is for high heritability. It has to do with the amount, the proportion of genetic variability. That's what it's all about. Does everybody understand that? We're dealing with that formula up on the top board. Low heritability means we've selected out everything here. There's very low genetic variability. Here, there are a lot of room to select, a lot of genetic variability. We can select for what we want. So there's high heritability, but it says nothing. Well, this curve says something about the milk yield. But heritability has no correlation to milk yield.
How much genetic variability?
The proportion.
Population.
It's the proportion of population variability to of genic variability to population variability. So this is all about population variability, right? And so we can estimate that from how it moves the curve. Here, now we can select out, and the curve is going to follow that population. Down here, because we're out there, variability is gone. It means, so H of 100%, H of 1 means that all the variability is G. That there's no environmental variability. And 0 would mean that, so that 3% conception, near 0, means that the variability is due to the environment. In this case, is there a male around? But there are genes that affect fertility. And so it's not 0.
So you said like H equaling 0 is very low to the environment and 1 is due to certain genes?
Yep.
Okay.
But you almost never see 0 and 1. I mean, it's always going to be a mixture. And those are extreme examples.
So if a cow was milk yield, would the environment be like hormones they get to make them produce more milk, or is that part of
Say that again.
like with milk they use hormones
Um,
sometimes to get them to produce more milk? Is that an environment or
I think it's the whole genetic system leading to lactation, which is what some cows give greater yield than other cows. part of that is their alleles. We're not changing the genes, we're changing our alleles for higher milk yield.
So that's the 43% coming to produce more. And then
Right, so average, typical heritability for milk yield, you know, we can find the extremes, but that's the average. Yes?
You said if H equals 1, it's decided by the genes?
If we have high heritability, if H equals 1, that says that the variability is due to the genes. You always have to phrase it, the variability is due to genic variability almost entirely at H equals 1, 100%. Whereas midway on the curve, it would be 50%, half due to gene variability, half due to environmental variability. Anybody else? Any last questions before we move on? So far in this course, we've looked at the nature, the function, and transmission of genetic material. That is, we've been looking at Mendelian inheritance. One of the goals of science is to relate what's done in the laboratory to outside the lab, to the real world. Mendel did the experiments that he did to come up with the nature of transmission by strictly controlling the alleles that he used. He used tall and short, yellow and green, and Mendel strictly controlled the mating scheme, so he established which plant he was going to mate with which other plant. And again, that's not the way real-world populations live in nature. And so what we would like to be able to do is to look at how or what the rules are for transmission of genes in a real population. For example, there are more dark-haired people living in Italy, more blonde-haired people living in Sweden. What determines that ratio of hair color? Why is it so different in two different countries? How can we establish the rules that control the phenotypes, not in a laboratory setting, but in a real-world setting? So that's what we're going to look at. Understand that in the population in Italy, where there is predominantly black hair, and the population in Sweden that has predominantly blonde hair, that the genetics are exactly the same. And so we have these terms, dominant and recessive, and now we have a new term, predominant. You know the definitions for dominant and recessive. Predominant just means which allele is most numerous. So the predominant allele, the predominant hair color allele in Sweden is the blonde allele. The blonde allele is still a recessive allele. So what we have to ask then is, can we come up with a set of laws, a new set of laws that extend beyond Mendelian genetics? Mendelian genetics explains very, very well how a pair of alleles flows from two parents to one child. What we need now at the population level is a set of rules to explain predominance of certain alleles in certain populations. And so what we see in Sweden, we have an equilibrium established where blonde becomes the predominant allele. In Italy, we have a different equilibrium established where dark allele, the dominant allele, is the predominant allele. And so what we want now is to be able to describe equilibrium frequency. We want to be able to describe the rules that determine which allele is predominant. We know the rules which determine which allele is dominant and recessive. So there are a number of factors that control the equilibrium frequency. Mutation rate. Mutation rate in this example is mutation from dark hair to blonde. So loss of color is typically the recessive. Selection. The mating choice is not under the control of an individual. Migration. As more Italians migrate north, it's going to change the equilibrium frequency. And finally, the last one, drift. I'm not going to explain now, but we'll take it up after we go through the first three things that affect the equilibrium frequency. The forces that affect the equilibrium frequency: mutation, migration, and selection. Those determine what the population structure is going to look like. So Mendel gave us rules for how genes flow in individuals. We need a new set of rules to explain how predominance, how alleles flow in populations. Any questions before we look at some populations? Okay. This is a study. This one is from an urban white American city. So let me backtrack for a second. Blood groups are very easy to do in terms of population studies. So many people have blood groups. However, ABO is not a suitable system for what we want to do. It's a complicated system of dominance and recessive characteristics. A and B are codominant and dominant to O, and so that makes things very awkward. RH plus, RH minus, we don't want to use because there's a thing recessive. The minus is recessive. Instead, we are going to use the MN locus. You had a question?
I was about to say that M&M locus.
I'm sorry?
I was about to say M&M.
Right. So M&M is a good system because these are codominant. Somebody who is heterozygous, just like AB, has an MN phenotype, and so you can see each allele. So population structure, everything in this chapter is going to be about population structure. So we're going to look at the genotype, M, N, N. 1787, 3039, 1303, 6129. That's the population structure of the MN locus for 6,000 and some people. Everything in population structure is about the allele frequency. That is the key to everything which will allow us to determine population structure. That's going to be the number one thing for this entire chapter. So we have two alleles. We have an M allele and an N allele. How do we calculate the M allele frequency from that population data? What's that?
Divide how many of them are total now?
Okay, so how do we calculate, how do we find out how many M alleles there are?
You multiply the frequency for the phenotype MM times 2, because there's 2 M alleles for that phenotype, and then add the frequency for the MN genotype.
Okay, I don't want to multiply though, so I'll just say, I'll take what you said and do it out. That's the effect of multiplying by 2. Plus, we have to add in 3,000 of the heterozygotes, because the heterozygotes have one M allele, 3039. What's the denominator? What's the denominator? No, it is not 61. Times 2. Why times 2? Because we want the allele frequency, and each one of the 6,000 individuals has 2 alleles. So we multiply the number of people by 2, which is something. 12,258. So this comes out 0.54. We're going to let this equal P. And so we're going to use for allele frequency P and Q. In a normal system that's dominant, P is going to be the dominant allele. But we're going to stay away from dominance as much as possible, just because we want to see everything. And so now, how would we calculate the N allele? Give me the numbers. How do I get the N allele frequency?
1303 times 2 plus
What's that?
1303 times 2 plus 30
1303 plus 1303
plus 3039
plus 3039
over 12,250.
divided by 12,258 is equal to 0.46, is equal to 2. Everybody see that? Any problem? So, this is equal to 54% P allele, 46% Q allele. Anytime we have this percentage means that we have a probability. So, because we have a probability, we can go backwards and ask, what is the probability of M, knowing what the probability of M is? The probability of MM is 0.54 times 0.54, which comes out to be something, which comes out to be 29%. You can calculate the probability of N heterozygotes, 0.54 times whatever 46, which comes out to be something else, times 2, times 2, right? Because you can have an individual who is MN or an individual who is NM, right? Everybody agree? So you have to multiply that by 2. That comes out to 50%, and then the probability of N is 0.46 times 0.46, which comes out to 21%. If we calculate this, what we have is 29%, 50%, 21%. So, what this means is we can rephrase that as P squared plus 2PQ plus Q squared, where P equals 0.54 and Q equals 0.46. Anybody recognize that?
A squared plus 2ab times.
That's the old binomial, which says that we can take the allele frequency P and Q, and according to that, we can use the binomial P squared plus 2PQ plus Q squared to calculate the population structure. This is going to be the central theme, the central tenet of this entire chapter. That we can go back and forth, we can take the population structure, here's the population structure, we can take that, calculate the allele frequency, and that allele frequency can be described by the binomial here. Now, for this population, it kind of looks like a 1 to 2 to 1 population. But just to convince you it's not, let me take another one, which I happen to have here. I can't raise that bottom board. So let's do a second population. This is a population out of a New Mexico Native American village. The phenotype M 305 and N 52 and N 4, 361 individuals. So clearly, and I wish I hadn't used that bottom board, clearly a very different looking population structure. The first one was almost 1 to 2 to 1. This is skewed heavily in this population. Different population structure, just like Italian dark hair and Swedish light hair, skewed heavily towards M. Any questions on this so far? So again, you can get P or M is equal to something, 305 plus 305 plus the M's in the heterozygote, 52 divided by 2 times 361. This comes out 84%. So you can get Q Yes, sorry, I looked at the wrong number. You can get Q, which is N, which is 52 plus 4 plus 4 divided by 7.2, which is 0.08. And so now we can do the exact same thing we did before. We can take p squared plus 2pq plus q squared. So 0.92 times 0.92 is p squared. That comes out to 84%. 2 times 0.92 times 0.08 comes out to 15%, and 0.08 times 0.08 comes out to 0.007. And so these numbers are 84%, 14%, and 1%. And so the whole point of this is that we can take these two populations, the urban population, which has an almost 1 to 2 to 1 ratio, not quite, and this Native American village, which is very heavily skewed. And even though it doesn't look like this fits the binomial, it clearly fits the binomial. The data is almost perfect. This is kind of skewed because that's so small, but nonetheless, this is a perfect fit. So the binomial means random chance distribution. The binomial means that there is virtually no selection. Now you might think that for blondes and brunettes, there is selection. Men prefer blondes, so they say. But here, nobody knows the blood type. And so the selection is completely and totally blind. And so what that says is that for both of these populations, whether or not it looks like it's a binomial, that this rule here is the rule for how to convert allele frequency into population structure. I had that on the bottom board, but I need to write it again. You can go from the allele frequency to population structure by the binomial. And you can go from population structure to allele frequency. So this is the be-all, end-all, do-all for this chapter. Everything that we do in this chapter is going to be about going back and forth between allele frequency and population structure, and the binomial is the key to how that's done. Any questions on that? So this rule, this is fully the equivalent of Mendel's laws. Mendel's laws govern how alleles flow from your mother and father to you. The binomial rules how alleles flow in populations. This was seen way back in 1908. By Hardy and Weinberg,
Pretty cool.
And is now called simply the Hardy-Weinberg law. Remember that Mendel's paper was discovered in 1900. And huge publicity, worldwide. People all over the world were investigating now genetic inheritance. And Hardy and Weinberg did exactly what we just finished doing. They were looking at allele frequencies in populations. And after a few trials, just like Chargaff noticed a pattern, Hardy and Weinberg saw the pattern, that one can describe the population structure by the binomial equation. There's actually an interesting corollary. Called boundary theorem. So because of this law, that if you know the allele frequency, you can calculate the population structure. If you have the population structure, you can calculate the allele frequency. There's a caveat to that I'll tell you in a second. Founder effect is what people see on islands, mostly in the Pacific, because that's where most of the islands are. But the Galapagos and the Hawaiian Islands are famous. They're isolated, they're volcanic, so they erupted from the seafloor, in some cases millions, in some cases hundreds of thousands of years ago, as barren, bare rock. And then whatever drifted, flew, or swam on that island, they founded the population. Their alleles, that founder group of individuals, their alleles set the population structure. That's why the different islands in the Galapagos have very different population, not very different, they have the same species, but with different characteristics. The same thing is true in the Hawaiian Islands. Again, found the exact same way. It's a volcanic chain. The Earth moves over it. They keep popping up new islands. If you're around in 100,000 years or so, there'll be another island just to the east of the Big Island. It's on its way up from the seafloor. So founder effect is a nice corollary for Hardy-Weinberg. Now, Hardy-Weinberg law has a condition. And that condition is there must be random mating. But you say human population doesn't mate randomly. Your mate is not selected for you by a lottery. But the population is so large that it doesn't matter. Clearly, whatever population, as long as it's a pretty random population, people living in a city, a whole city, is under Hardy-Weinberg law. There are some interesting exceptions to that in nature, because Hardy-Weinberg law really does depend on random mating. A wolf pack does not obey Hardy-Weinberg law. A lion pride does not obey Hardy-Weinberg law. In a wolf pack, the dominant male gets all the matings with the females. In a lion pride again, the dominant male gets all the matings. But if you take all the wolves in Alaska and do this genetic study, you see the Hardy-Weinberg law. So an individual pack may not be random mating, but the wolves of Alaska, there's enough gene flow between wolf packs. The same with all the lion prides on the Serengeti. A lion pride is not doing random mating, But in both those situations, the males are usually thrown out and they go into other packs. And there's your gene flow, which randomizes the population. Any questions on Hardy-Weinberg law? All right, so this says that once we know the allele frequency, that's the population structure. It implies that population structure is fixed. Is population structure fixed? It is not. Why is population structure not fixed? Why is population structure not fixed? Say that again. Okay, tell me how. I want to know details. What's that? No, not good enough. Predators are random. No, random. Migration. What else affects alleles in a population? Genetic drift. What else affects alleles in a population? Mutation. What else affects alleles in a population? What's that? No, not really. No, that's pretty random. Selection. Those four that I gave you about 15 minutes ago. Those are the forces. Oh, I have too much red. Those are the four forces which change population structure. That's why Italians have a different population structure in terms of hair color than Swedes. It's these rules, those are the forces which change allele frequency. Although what we'll see is that drift is kind of different. Drift really isn't a force. We have to handle that differently. Any questions on that? Friday is the exam. I've already put the old exam in the conference center. I'm doing the health session tonight. Ivana's doing the health session. Not tomorrow.
So I wrote a poem about video games. Can I get something at Ubisoft?
Huh?
Go to both rooms twice to make sure.